Effective spray application. From uncertainty to confidence. This video presentation covers the components of an effective spray application, the uncertainty imposed by complex field conditions, and the opportunity to eliminate uncertainty using models and decision support tools. Imagine a conventional air blast spray application in an orchard or in a vineyard. The objective is to apply pesticide on the tree or vine canopy as the target for pest control. Hence, the spray application is considered effective when it leads to successful control of the target pest in question.
The amount of pesticide that is properly placed on the target, where the pest resides, will perform the pest control activity. That is, only the spray droplets that reach the canopy and are captured by the canopy are available to actually control the pest. The total volume of spray captured by the canopy is what is loosely called the on-target deposition or canopy deposition. The remaining spray that ends up on the ground or that drifts to unintended locations are considered lost. It is therefore important to maximize on-target deposition while minimizing ground loss and drift loss. This does not simply mean increasing the amount of spray applied, but rather optimizing canopy deposition.
So, if the tree canopies are not large and touching like these, and are not continuous hedgerows, but are medium trees with disjointed canopies, or are small trees with disjointed canopies like these, then, a smart sprayer that stops spraying when there is no canopy is an ideal equipment to use. Although not all growers and applicators may own or have access to this type of sprayer.
Also, if the trees are not as large as would need all, or most of the nozzles to be spraying as in this scenario, and leaving some nozzles on will waste spray material, as in medium-sized trees like these, or in small-sized trees like these. Then, the nozzles whose spray miss the target must be closed as shown here, or here. This can be achieved automatically by using a smart sprayer with canopy sensing technology. It can also be done manually by making the adjustment during sprayer calibration prior to the application.
These are only a part of the precursors for an efficient and effective spray application. Overall, there are three components that account for an efficient and effective application: the sprayer, the spray, and the operator or crew. The sprayer must be well maintained, well calibrated, well adjusted to the target canopy, and well operated. The spray application must be properly timed, considering the target pest and the weather. And, the spray must be accurately applied, well directed to target canopy, must adequately penetrate the target canopy, and be optimized for on-target deposition and coverage. And for the sprayer operator or crew, they must be well trained and knowledgeable, be familiar with best practices and adhere to them, and be attentive and quick responding.
But even after taking care of all of these, the outcome of the application can be uncertain due to the complex interaction of the influential factors. How can we estimate on-target canopy deposition and off-target ground loss and drift, for planning and evaluation purposes, for the wide range of situations that could exist? Different tree characteristics, different orchard conditions, a wide combination of application parameters, and a host of weather conditions. Even with several years of experience, this is practically impossible without using a tool.
And that is where utilizing a decision support application such as a web-based or mobile application can be very beneficial. The general objectives or benefits of decision support tools include increasing awareness and control of critical factors, reducing uncertainty in decision making, improving efficiency and speed in decision making, providing competitive advantage, and facilitating communication.
Some examples of spray decision support tools include Dosavina, which is a tool for determining the optimal volume rate for pesticide spray application in trellis vines based on the adapted method of leaf wall area. Citrusval, which is a tool used for determining the optimum spray volume rate for pesticide application in matured citrus. Orchard Max app, which uses the crop-adapted spraying model to match pesticide rate pre-planted area to the size, shape, and density of apple trees. And Citrus SprayX Expert System, Spray Evaluation, which simulates the Larbi-Salyani spray deposition model to predict % on-target deposition, ground deposition, and potential drift in citrus application. While the first three examples determine how much spray to apply, the last one determines the outcome, that is, how much you get out.
Through an iterative research and development process involving training, evaluation survey, and end-user feedback, to further develop Citrus SprayX, 2 web apps have emerged. AirBlast Spray Planner web app, which aids with sprayer calibration calculations similar to Citrus SprayX planning section, and AirBlast Spray Advisor web app, which simulates the Larbi-Salyani spray deposition model to predict % on-target deposition, ground deposition, and potential drift in citrus application similar to Citrus SprayX evaluation section, but with enhanced features and information. The rest of the presentation provides an overview of AirBlast Spray Advisor and the potential benefits of using this tool to minimize uncertainty during planning and evaluation of AirBlast spray applications.
AirBlast Spray Advisor web app was designed to provide decision support to allow for easy identification of best practices for improved effectiveness in AirBlast applications. It simulates the Larbi-Salyani spray deposition model, a mechanistic model based on the physics of dispersion which accounts for atomization, droplet evaporation, and spray interaction with the canopy leading to on-target deposition and potential runoff from leaves. The main output values are the predictions of canopy deposition, ground fallout, and potential drift. User inputs for AirBlast Spray Advisor include information about tree characteristics, orchard condition, weather condition, and application parameters. The specific inputs can be accessed by simply clicking the relevant button. These inputs were identified to be easily obtainable by the user, and default values are included to allow the user to be able to only focus on inputs that they are interested in, that is, keeping everything else constant. In the top right corner, the app displays derived application parameters as feedback during the simulation. In subsequent simulation runs, the What If pane at the bottom compares input and output of the last 2 successive simulation runs to show the user how changes made from the previous run affect the output of the current run. This way, the app does not give an active recommendation but rather simply shows the effect of the changes made in inputs on the outputs so that the user can make the final decision based on the results.
Here are the links to AirBlast Spray Advisor web app and a QR code for mobile access. Please note that the app is currently accessible only on PC, Mac, iPad, iPhone, and Chromebook. However, it is not accessible on Android and some other mobile devices. This presentation has been brought to you by the Agricultural Application Engineering, or ARGAP-E, program. University of California. Division of Agriculture and Natural Resources, and Department of Biological and Agricultural Engineering, UC Davis. Kearney Agricultural Research and Extension Center, Parlier, California. Thanks for watching.